Hi guys, today I'm going to talk about the odds ratio, and this video is really just to see how the lighting works out and the sound quality works out, because I already have a video on this topic, and the angle and I don't know, just to see how this works in my office. So odds ratio, the classic example of when you'd use the odds ratio is you have a 2x2 contingency table, you have two different treatments. You have A and B, and then you have the response that either worked or didn't. Response, yes, no. An example of that would be like comparing Zyrtec to Claritin, which would be allergy medications, to see if Zyrtec is more likely to work than Claritin if you give it to a random patient. I should use a different color. Let's erase that. So, Zyrtec, Claritin, I think it's TIN, I don't know. And then the response, we're going to say it noticeably reduced their allergy symptoms. It didn't noticeably reduce their allergy symptoms. So then you want to see so then the probability that Zyrtec worked is this cell count, the number of times it helped, divided by the total number of people. So if we say that there was, say, 100 people in the trial, or that were assigned Zyrtec, then we'd have something like 95 here to 5 here. For Claritin, this data is just made up. Say it worked for 70 of the patients, 30 it didn't work. To keep it simple for now, we're going to have it's a balanced design, equal number of patients in each treatment. So then we want to see if there's strong evidence that Zyrtec gives better performance than Claritin. So just looking at this data, it looks, Zyrtec performed better because these both it's a balanced design, so we can directly compare these two numbers. But are they significantly different or not? So I don't know, but I can find out using the odds ratio, or confidence interval for the odds ratio. So basically what we're doing for a 2x2 table, this is kind of oversimplifying it, but we're going to convert this into proportion with a variance. So this is going to be, if we just this isn't technically correct, but basically assume it follows a normal distribution centered at 95. And then it'll have whee. And then Claritin follows a normal distribution as well. Assume it's centered at 70. And then whee. So then we want to see if these two how different they are. And so then if we overlay these two, so basically we're doing like an ANOVA kind of overlay. You get So we have Claritin centered at 70, and we have Zyrtec centered at 95. And I know this is 0.9. Anyway, so we want to measure how different Claritin is to Zyrtec, how strong the evidence is that they're different. The variance comes from the total amount of data, technically from the cell counts. It depends if you use Anyways, the more data you have, the less variance, the stronger the evidence is that these two will be different if they are in fact different. And the less, if you only had like 5 samples here, 1 here, 8 here, 3 here, you have very small cell counts and you're going to have very wide variance in the sampling distributions. And then it's much harder to show strong evidence that they're different, even if so in this case, this is 95 to 70. The difference in probability is 0.25, 25% difference. The 25% difference, if that's the true difference, it's easier to detect if you have larger sample sizes. So anyways, let's get into some details. So that's when you would use it. You're comparing treatment A performance to treatment B, and essentially you're comparing this cell's performance to this cell. And when would you not use it? So an example of data that's set up in a contingency table, but you would not use a odds ratio, is something like this. You have data, you have the true status, diseased. So you're looking at diseased plants per se, so you know if the plant's actually diseased or not. Say you're training an animal and it sniffs it, and by its smell it can identify it. It can predict if it's diseased or not. So then animal prediction, disease, not disease. So now we want to measure. So we have the true status of the plants. They're either diseased or they're not diseased. And we have the animal's prediction that it's either diseased or not diseased. So this cell, if the animal predicts it's diseased and it's actually diseased, that would be a correct prediction. If the animal predicts it's not diseased and it truly is not diseased, that's correct. But if the animal predicts that it's not diseased when the plant is in fact diseased, then that's an incorrect prediction. And the same thing here, if the animal says it's diseased and it's not diseased, that's incorrect. So if, in this case, if you assign the null is the tree's not diseased, and then the type 1 error rate alpha would be predicting that it's not diseased when it is in fact diseased. So this would be the type 1 error rate. Type 1 error rate, and this is what's called the type 2 error rate, which is concluding the null when the alternate's true, and type 1 is concluding the alternate when the null's true. Anyways, odds ratio does not apply here because odds ratio essentially compares the probability of this prediction to the probability of this prediction. And if we calculate that, you're not really comparing apples to apples. What we're really interested in is comparing this to this, or looking at the type 2 error rate or something. But anyways, in this example, the odds ratio wouldn't be meaningful because the odds ratio confidence intervals are really testing for equivalence. You want to see if treatment 1 is equivalent to treatment 2. That's not really what this data is in this format's measuring. So if you calculate an odds ratio for this table, it's not really meaningful. So don't use an odds ratio for this. But getting back to the odds ratio, so how do you calculate the odds ratio? So I should have led with that actually. The odds ratio, so we have the response and then say yes, no, and the treatment A versus treatment B, and we want to compare treatment A's performance to treatment B. So odds ratio, I kind of did a poor choice of notation calling this A and B, because the classic notation is to call these cells letters. This is cell A, cell B, cell C, cell D. So the odds of A giving a yes response, odds of A is defined as A divided by B. The probability of A, given your odds are related to probability in that, so the odds are of that, and given that you're assigned treatment A, the probability of having a correct response is A over A plus B, which would be the total number of people in the row, which would be A over 100. So if A was 95, it would be 95 over 100. But we don't work with probability for odds ratio stuff, because for a lot of categorical stuff, because odds are more natural for the mathematical formulas and more easy to work with and convenient. So we work with odds. Anyways, the odds of B is equal to C over D. Just this cell divided by that. It's a measure of how much, it's basically for abuse of language. It's basically a probability, given your assigned treatment, B, it's the probability that you'll have a yes response. Technically, it's the odds that you have a yes response. The odds ratio is pretty much like the name implies. It's just the ratio of the two odds. So it's usually denoted by OR for odds ratio, which equals odds of A divided by odds of B, which equals A divided by B over So that's how you calculate the odds ratio. It's a D. It's really easy to do. In fact, this times that divided by that times that. It's also known as the cross product. It's basically a 10th grader could do it. And nothing hard there. But now how do we get these confidence intervals? If you ever use SAS or SPSS or R or whatever, it'll usually also spit out a confidence interval. It'll calculate the odds ratio and a confidence interval. And you see these come up if you use logistic regression or something like that as well. I don't know why I just erased that. So now I'm about to do some mathematical voodoo. This isn't quite how it works, but first, to sort of explain where the confidence intervals come from, I'm going to pretend some stuff works in a way it doesn't work. So if you pretend A follows a normal distribution centered at 95, because we observed 95, woo, and then this follows cell B follows a normal distribution centered at 5, because we had 5 observations there. Then cell C follows a normal distribution centered at 70. And D is centered at 30. So the odds of A is equal to a distribution centered at 95 divided by a distribution centered at 5. And then if you can guess what this resulting distribution will be centered at, it'll be 95 over 5. So the resulting distribution should have a center at 19. So the actual shape technically won't be normal. A normal distribution divided by a normal distribution is not normal. If they're centered at 0, it becomes a Cauchy distribution. I don't know how you pronounce that. Anyways, which is kind of normal shaped, except it's not defined at 0, because 0 divided by 0. So normal distributions can take on any value, and so you get 0 divided by 0, which causes a big problem. Anyways, if they're not centered at 0, you get some other distribution. If you Google ratio distribution on Wikipedia, it'll actually tell you. But basically, it's basically going to be normal shape centered at 19. It makes sense that, because we know the odds of A is this divided by that, which is equal to 19. So the odds of A are 19. So it makes sense that we'd have a distribution centered somewhere about 19. So 19 plus or minus some amount if you calculate the confidence intervals for the odds. So if you were to calculate the confidence interval, it would make sense that it would be in the form of 19 plus or minus some value, where we just exclude these tails. So that's reasonable. The actual shape's pretty complicated to actually find the exact shape, but the basic shape's going to be approximately normal distributed. Then the odds of B, very similar to what you just did for A. It'll be 70 divided by 30, which is 2.33. So it'll be 70, that's really bad, divided by a distribution centered at 30. and then we do the algebra of random variables, and then ignore what actually, there's a book right here on the algebra of random variables. And then it'll be centered at 2.33, because that's this number divided by that. And then it would make sense if you were to calculate confidence interval, it would have to include 2.33. So then, doing more voodoo math, the odds ratio would be this distribution centered at 19 divided by, or that includes 19, divided by this distribution that includes 2.33. And so if we actually calculate the odds, which I should have did, the odds ratio, the odds ratio is equal to, in this case, 95 over 5, that divided by that, divided by this over that, 70 over 30, which is equal to 19 over 0.33, which is, I think, 7.69, I don't know, something like that. So then the odds ratio, we're going to give this a distribution. The variance is a function of these cell counts, and same thing with here. And then eventually, we'll actually get something centered at 7.69, and it'll be approximately normal shaped. And so then that allows us to calculate a confidence interval for the odds ratio, and say a 95% confidence interval for the odds ratio estimate is this, and the 95% confidence interval goes from this value to that value. So that's sort of how it works. It's not actually how it works. Actually how it works is we assume these cell counts are binomial or Poisson, because you can't have negative cell counts for cell count data. That doesn't really count data. That doesn't really make sense. You count the number of times something happened to how many patients something happened to. We can't really have a negative number. So first, we actually scratch this normal thing, unless you're doing the asymptotic distributions. You can do an asymptotically normal one. But anyways, so we scratch that, and then we say this was 90. We say that these cells follow either binomial, Poisson, or you can also do negative binomial. That's not that common though. So then sort of the kind of algebra of random variables, you take a function, a distribution, which is a function, divided by another distribution, and that results in another function. To do that, you have to get into some Mellin transforms and fancy mathematics, because it has to integrate to one, and it's not real intuitive to do. It actually gets into so anyways, the binomial distribution, the variance is determined by the numbers. So in binomial of n, p is a probability, n's the cell count. If in that case, here for cell A, it would be binomial of 195.95. So then the variance for that cell, variance of cell A, would be NPQ, which would be 100.95.05. And you can calculate that, and this cell has a variance. It will also so happen that this cell will have the same variance. This cell will have a variance that's different from these. This cell will have a variance that's same as this, but different from the top row. So then you have a point estimate and then a variance or a binomial distribution shape. And same idea applies to the Poisson if you assume they follow Poisson distribution, also for a negative binomial, except you can manually adjust the variance in those. And then you can get exact confidence intervals using these assumptions. Or you can use some asymptotically derived formulas to going off topic to random variables. If you have algebra of random variables, so if we have variable x that has some distribution divided by variable y, and we want to find out what that's equal to, let's denote that as the PDF. Let's say we're looking at the PDF formula. F sub z of z is equal to integral a infinity to infinity absolute value of y. I think it's y. F of z zy y dy. Zy comma y dy. So I think it's either zy y dy or zx comma x dx. I don't remember. I have to look it up. But you calculate the joint distribution of these two. So that's this f of x, y. But then we let x or z equal x over y. That yields x is equal to zy. So then this is x, but we're writing in terms of y dy. So then we, for a value of, so the resulting distribution, this is distribution, this is distribution. So if you want to find the probability at a given value of the resulting distribution, you do the absolute value of y, you're integrating over y, times the value you're inputting, times y in the joint distribution, comma y dy, and then you integrate it. And so we have so this is, say that's x, this is y, this is f of x comma y. So then we're going to integrate this whole thing every time, but when z is very small, if this is centered at 0, when in the case where the joint distribution centered at 0, it peaks at 0, the mode's at 0. When z is very small, this moves very slowly, so you're integrating over y, but you're integrating in the z direction over y times a small number, so it progresses very slowly. And in that case, it spends a lot of time. There's a lot more area. You're effectively, if z's are a fraction like 0.5, this becomes twice as wide on the z-axis, so the area becomes twice the area. And so that gives it a lot of weight towards the center, towards the mode. And then when z becomes very big, if this is like 3, over the x-axis, it covers the whole x area in 1/3 the amount of y distance, and so it gives very little weight when z gets large. And so the result of that is it puts towards the center, it gives it a lot of area, and far from the center it gives a little area. And then you integrate it. You have to repeat this integral for every z value. So if z is discrete and it runs from 1 through 10, when z is or 0 through 10, you can have a cell count of 0. Cell count of 0, you integrate this. Cell count of 1, integrate this. Cell count of 2, plug z in, integrate it. Repeat it a bunch of times, and it'll actually give you the PDF of the ratio distribution. So that's it for the odds ratio. Bye, everyone.